yeah, I think we started the stream. So I'm gonna set up a bit before we can do our stuff. Yeah, I think it's working. So I'm gonna test the sound because the first few streams not like, it's very bad with the sound, it's very low. So I'm gonna test it out. Is it working or not? Hopefully it is. Oh god. Still sound very low. I'm gonna put the mic here instead. Hopefully you can hear me. Alright, what is this stream about? I forgot. Okay, so it's the 8-bit one, so where were we last time? I already forgot. It's been like 3 days or something since I streamed my last 8-bit computer. Oh god, this is a mess. So where do we live off? I think we did something with the Figma. Okay, this is it. Oh, this computer screen is very bright. So last time I tried to redesign the computer architecture, I think, and we use something like loader ROM and microcode ROM. These are two different ROM that correspond to different action in our computer. I think I already forgot what's going on. So I think last time we have some problem figuring out how to run the program. I'm not sure what is going on. So our first problem is something related to control flow over here. We have a basic, I call it the start of the computer, the loader, but it's not really a start flow, because we have the loop over here. We go back and then we run this again for the next instruction in our RAM, for the next instruction. So it's not really the start. And we're having problem figuring out how to run each of this step in here. And I use something like a decoder to decode the control code and to control each component. And I found out that is a bad decision, because I realized that some of this what do we call them, operation or something like that, some of this could be run together. So I can output enable the program counter, and then I can read enable the RAM manager at the same time with the program counter, and then the value will be automatically go through our RAM register. So if I use a decoder, we can decode a binary value like this, and into it's converted into 16-bit, but only one of it is enabled, so we cannot control 2 or 3 at the same time. So I think we're going to not using this technique anymore, and we looking at Ben Eater design, his 8-bit computer design, and I wonder about this clock thing. You can see how do I zoom in? CLK. We can see that every component has CLK thing in it. So I watched his video, his series. Basically the CLK is just a clock signal to every single component. So what if I, for example, if I want our RAM to read enable a address something in our 8-bit bus, I just put the 8-bit bus, the address inside our bus, and I enable our read enable, and then the value will not go into our RAM yet. It's not going to work yet. So we have to enable the RAM manager. We push like a single signal into our component in order for it to work what we wanted to, like what we wanted. So what he doing is that every single component in his computer has the clock signal. So whatever he do, like whatever instruction or operation, it need a clock signal to work. So for example, if I want to output the address from our program counter into our RAM, so I enable the output of the program counter and enable the read enable of our RAM manager. The value will be stay in the bus. It's not going to input directly, like instantaneously, into our RAM manager or RAM register yet, until we enable our clock here. So basically the clock make it synchronize, work at the same time together. I'm not sure you understand, but I think that this stream is just me building the computer, but I spent so much time explaining and redesigning the thing, and we haven't got very far. So he has something like the control logic, CPU control logic, which is very important. So basically, I already forgot what he did. So every single flow over here, like we can call it flow, we have a simple, like we have a sort of pattern over here. Basically we read, we get the instruction from our RAM. Why it's so different here? So we can see that this top over here is to get instruction from our RAM, and then after that we just take whatever instruction from our microcode ROM to run it. So what he did is that every clock, it's not actually a clock pulse, I think I'm gonna start drawing it up. Maybe it make more sense. So let's start again. I don't know how many times we start again and again. So this is what we have so far. Let's redesign our RAM. I did draw some diagram on my note over here. I don't want to. So basically I'm going to redraw redesign our RAM. I think last time we have a read enable and write enable and value RAM enable. And we have the enable. So what we're going to change is from this enable thing, we don't call it enable anymore, let's just call it clock, like what we have over here by Ben Eater. I still don't know how to pronounce his name, but yeah. So we call it clock, and this value RAM enable, I think I can put it into a separate sort of bus, because we can have multiple chunks of RAM. Basically we can, I did some research on what chips we can use. So the problem is Mr. Eater I don't know his name. So he recommend to use RAM. I think how do I say that? I mentioned it once before about the difficulty of finding RAM IC chip. What is it here? So using these chips over here, 74189 chip, and I cannot find anywhere that I can buy it. It's like on Amazon, on any online shop selling there's a Mouser, I think, also a place where I can buy electronic component, but I cannot find the exact same chip. So I did some search, some googling. They recommend me to just search for SRAM. So SRAM basically a static RAM, random access memory, and we can search for 8-bit. Is it this one? Let's just click on one of this. So, and we need a data sheet to look at it. Yeah, so we kinda get some overkill result over here, because the RAM we got here is, where is it? It is 8-bit, but we got 32K, which is 32,000 byte, which means we got 8 times this much of memory. So we get 32,000 byte of memory, and what we going like the first what, oh my god, I'm horrible at English. The initial idea of building this RAM is just like going to be 8-bit. I was going for 8-bit, not this much. So 8-bit is something 256, which means that we can represent our RAM address in, let's start over. We can represent our RAM address in 8-bit, which is around 256 address, which means we have a 256 block of memory to work with. But I split it into 256, and I have another 256. Now we have a 512 or something of RAM, but one of it is for the instruction, only instruction, and unable to change anything, I think, or maybe we can change it. And the other one is value RAM. I call it the value RAM. Basically it's just sub op, like not sub opcode, it's just the RAM that stores some value necessarily to do calculation, like for some random program. And on top of 8-bit address, we have another bit that choose which one of these RAM that we're going to work with. I just say anything in my head out loud right now. Not sure you understand, but yeah, let's go. Maybe that will help. So this chip, you might use only a few, like only 8 pin of address. I'm not sure it's even available that way, so we have to read the pin in and pin out. So we have A0 to 8 to 12. So basically it is 12 bit. What 12 bit? 2 to the power of 12, basically to 32,000 byte. Let me do some calculation. I don't know how to. 2 to the power of 12. So it's 4,000. So it is a lot, but I'm not sure why they put only. Wait, something wrong here. 32K. Oh, it's not 12 byte. It is 13, including the 0. Godness. So it's 80. 8,000, not 80, and it's still smaller than this one. So I'm not sure what's really going on. Look like we have 13. Wait, there's another pin over there. So it's not 13, it is 15. Yeah, that's what we have. So we're gonna use only 0 to 7, and we have the 8th one, the A8, the address number 8 is for V, for this thing over here, VRAM enable, to choose which chunks of this. I don't know why I split it, but I think it's good to split it this way, because we like isolated the instruction from the value. So we kind of have a new architecture here. It's not really new, I think somebody already done that before, I think. Never heard it before, but yeah. So we have this chip in stock of about 2,000. I can buy it. It's not that how much for one single chip? Call it chip a lot. So about $6. Not going to buy it now, but yeah, let's get some idea what we're going to do. What is this? Let's check out this one. This one has a lot more size, memory size, than the last one. Yeah, so that's what we're going to use. So I think drawing is more better than using Figma. So I have a chips of RAM. Oh god, use this to make it. And we have a 8-bit of address connect to our RAM manager. I call it the RAM manager, but actually it should be only RAM register, because it stores the address of our RAM. Let's see what we're going to have. We have the read enable and write enable. So the word RAM manager is good because we can use it to manage all of this input. So basically what a Ben Eater has, he separate, what is it, the entire schematic. So he got the where is it, the RAM over here, the write and read enable, all the with the RAM. But what we're going to do is to create another component that handle the write and read and those stuff, that control our chip, RAM chip. Oh, I think we made a mistake here. Gotta move it a bit down. Yeah, Just go a bit to the middle so you can change anything later. So I think we're going to draw also the inside of our RAM manager, so use a different color. I don't know how many times we're drawing this, but redraw the thing could make our brain go bare, could think a bit easier. So what we're going to have this time is not going to be read or write enable directly. So in order to retrieve a data or update any data in our RAM, we're going to memory address register input enable first, which means that we're going to put the address into our RAM first. So now we have a separate step. So if we want to go from that address into a different read enable, the bus doesn't overwrite data, so the data on the bus will be already gone before the read from the RAM. Oh, okay. So this is just a 8-bit register. We could have more in the future in case we want to expand our size of our RAM, but for now it's 8-bit register, and the register is very important in 8-bit in any computer to be general, because it store basic data that necessarily to do some computation. So I think we should talk about the register somewhere. What was the register going to be look like, because I'm stuck right now, I don't know what to do. So the register is 8-bit, so we're going to have input 8-bit. So this one is 8-bit in, and we want the address, the value from our register constantly connect to our RAM. So we have another 8-bit connection over here. So this one is 8-bit out. Call it the 8-bit out. So if we input some 8-bit value 0001, this is only 4-bit, but we ignore the rest. So if we input it, we our register still have the same value, it's not changing. So we have to we have to make an input ourselves, so that input, we have to enable that input in order to change the value of our register. That that is more create a structure that very useful next time. So it's called the register enabled. So that's an idea of how we're going to do rack enable. So this is what is it again? RAM register, RAM address register. So RAR. We're going to have an 8-bit connection with the 8-bit bus. So I'm gonna make it a bit further. That way. This is our bus. We like bus because it connects everything together. So this is 8-bit bus. We'll delete this, and we're going to have an input coming out of our RAM address register, which we call the memory input enable. Call it the address enable AE. So the address enable, we have to enable it in order for our RAM address register to get the value from 8-bit bus into it, and then 8-bit bus will have to connect to, it's not that 8-bit bus, the register itself will have to connect to our RAM. Yeah. So now, for example, if I want to retrieve the data from address row 1, I ignore the other 4-bit, but let's pretend it is 8-bit. So I just put it into our bus, and then I enable this thing, which means that now our register will take the values, we still have it, into our RAR 1, and that RAR will constantly output the value of 0001 into our RAM, and the RAM still do nothing with the value. We need to like enable the output or input before it do something with the address. So now even our bus changed to a different value. For example, only 0 changed to empty value. It still has the 0001 in there, and it's constantly connected to our RAM, which is good because now our RAM might have something like the read enable, which basically if we enable it, it will output the value into the output pin, like this one. So if we enable the read enable, it will take the address 0001 into the RAM to go to the chunks of 0001 to know what is the value, and then it will output that value into our bus, and now the bus will change to the whatever value in that chunks of RAM. So that's great. And we have another pin, let's call it pin from now. It's called the write enable. So if we enable it, whatever value in the bus will put directly into our chunks of RAM with the address of 0001. Yes, so that seemed to be working fine. Now what I want to do is to connect this read and write enable into our, make it closer to the RAM. I don't think that we need this. I don't think we need to do this. But there's just an idea of creating a RAM manager. So this should be the address enable. AE, and this is should be just read enable for now. And we have another one coming out. Which is write enable. So let's put it together. Read and write enable, and we have the value RAM, which is just additional wire from our address. So our address is from 0 to 7, and the A8 should be, what do I call it, the value RAM enable. Oh, this is messy. I have to properly align this. I don't think we need the RAM manager at all. Why do we have this in the first place? Oh yeah, because I thought of some complicated stuff, and now it's not complicated anymore, because we have the separate thing of the RAM address thingy. So this two is read enable and write enable, and this is address enable. Let's write it down in case I forget in the next stream, and avoiding from try to prevent from redraw the thing again. And this is the value RAM enable. So value enable. Value enable, and this read and write. Okay, now we done with our RAM. Let's write it down. This is basically this thing over here. This is like, it's very important because we're going to use it connect to control logic, like what we have in, it's not V, like what this schematic over here by Benita again. So it will connect to the control logic, and basically what control logic will do is to pick one of this based on microcode. So we write the microcode for the entire computer runtime, like from the start to the end. It doesn't matter what kind of code is it, what kind of operation is it. Like, it doesn't matter if it retrieving the data or retrieving the instruction or just working with the instruction itself. So we don't care about this. This is just a bunch of junk that I created by me. And now I try, it's my attempt to create another junk, but hopefully it's not that big as the last one. So the next thing going to need is, I think it's program counter. It's what I can think out of right now. Bit bus. Let's close this schematic so that I don't look at it. Try to design my own one. So yeah, program counter, let's do it. Let's try our best without the help from Benita. So this address enable basically correspond to the clock signal from Benita's schematic, but we call it the address enable instead. Oh god, I just put some random stuff on it and now it's look so ugly. Oh man, what's going on? Alright, let's continue our stuff. Now we have the program counter. Destroy box. This time let's make it clean and make the computer from the schematic what we have right now. Let's erase this. This is a different color now. A wrong one. Doesn't matter. So our program counter will have basically the address of the instruction that we're going to work with in 8-bit. Connect to our 8-bit bus. But there's some catch. That address only out like into the bus if we enable our program counter. So this is the program counter PC, and we're going to have an input that is called output enable. Oh, what's going on? What has just happened? Yeah, but there's some problem right here. We don't have the clock to work with program counter, isn't it? We just output enable. Oh, so I think the clock only needed if we work with some with some write. Wait, we still need the clock, and now we don't have any clock at all. This is not clock, this is just input into our RAM, but every single one of these components will have clock. So this will be our clock line. And our program counter also have a clock line. Connect to it. We have to enable the clock in order to run whatever we're doing, so that it make every single component synchronize. Even the output from our control logic tell that we're going to enable the program counter, read enable the RAM. We don't care, just do it, but the value will not in the bus yet until we enable the clock. Now the value will put in back in, do some stuff that going to do. Yeah, and I don't know what I'm talking about, but let's go. Our program counter has another thing, which is jump. Oh, let's not talk about jump yet. Talk about the increment. The increment basically tell the program counter to go to the next address of our instruction RAM. So if we increment it, the program counter still do nothing until we put the clock in. Boop, it will enable, and then we can tell it to output enable. Yes. Yes, yes, sir. There's a bit of things here. What if I want to increment and output enable at the same time? So most of this is one. Clock in should be a bit of a transition between the older address to the newer one, but it doesn't really matter, isn't it? Let's not care about it. And we have the jump, which is very important for me, because we want our computer to be able to jump into any instruction. We will have an instruction that tell our program counter to jump, so that we can run like a loop in case we want to have a loop, or we can tell it to jump by condition, which means that it will jump if something. We will think about the jump condition later, but it will like make our computer become a general purpose computer that work with anything. Like we can create any program for it, whatever we want, if we have the jump by condition. Let now create the jump. So if you want to jump, we have to input some value into our 8-bit bus. Let's say 0010. It is number 2, I think. Yeah, number 2, the address number 2. So we put it into our bus somehow, I don't know how, but it could be coming from the RAM or from the control logic or other stuff. And then we have to enable the jump from 0 to 1, and then clock the thing. It will take this value, put it in. Yeah. I think that is it for the jump. Let's look at our sketch, older one. And we have the reset. Yeah, it's a reset. Also what we're going to need. So basically reset going to tell our program counter to start from the beginning, from the 000 address. I think we're going to connect this with our component later, but for now let's just put it like that. What we're going to need next. So I don't think we can continue now. We have to think about the microcode first. So let's think about our basic instruction retrieve flow. So if I want to retrieve an instruction from our program counter, from our RAM, first we have to output enable the address from our program counter. So here is the thing. So should we just say like that? So here's the program counter, output enable, and last time we can control only one of these, only one of these at a time. We cannot control multiple input because we use the decoder, so the control, like the microcode, will convert into one of the component line and control only one. Now if we use a different way of controlling all of this, we can control like multiple at the same time, but we need multiple bit of data to work with. So if our component has like more than 8-bit, we might use multiple ROM to store the code. What wire should we enable to control, to tell it to turn on, to turn off, or something like that. So now here's what we're going to do is we output it, but we're not going to wait for the next time step in order to read it into our RAM address register. We have to we can do it now. We can say, I should put this color correspond to the components, so R A R address enable or input enable, whatever. So while we output this, we can input this at the same time, so the value will be in the 8-bit bus when the clock enable, and then our register, RAM address register, will take the value in. So now we have the first time step. I don't think we can do the next step at the same time. So we have to wait for the next time step, which is take the address into our register and then read the instruction. So we're going to tell our RAM to read enable. So it is, let's put it blue. Read enable, and then the value in the instruction will come out, and then we can store that, we call it the opcode, which is basically the the code of what instruction are we doing now, like jump or load something. So we're going to store that opcode into another register. So I'm going to create one, and it is quite important. So let's call it the opcode register. So here's our opcode register, and it connects to our 8-bit bus. And it will have input enable. And output enable too, because we want to output it in the next step or something in order to retrieve it from the ROM. Read-only memory, if you don't know. So while we output from our RAM, we can tell our opcode register to, let's call it read enable instead of input, because it seems off. Now the value will come from the instruction in back, like from the RAM to the opcode register directly, store in there. And of course we need clock. And some of our opcode operation might need sub opcode. Basically, actually they call it the operand, and I just know it now. It called the operand, the second opcode that necessarily for the operation to continue. So the operation might need the address of the RAM to do something, to like load the value from the RAM or something like that. So the second opcode, but some operation doesn't need the second opcode. That is the problem right now. So we can store if it need or not in something. We need some component to tell our the entire computer that this specific opcode need a sub opcode or the operand. I'm not sure what we're going to use. So we can use ROM, and our ROM will store the value is sub, which means that we're going back to the older architecture over here, where we have is sub or not, and plus the rest with what is it going to do with that opcode. So let's think of it. So if it has sub opcode, we're going to run a few additional steps in order to get the value from our for the sub opcode, the operand. But if it doesn't, we don't do anything. We just continue with the instruction. So let's say it doesn't have any sub opcode for now. So the next step is that it will now our opcode is in the register, and the register will have some value, and now that value can put it into the ROM. So let's just quick thing over here, ROM, microcode ROM. So it will connect to the ROM. So it from 0 0 like 0 0 0, and after we read this two step, like after we done this two step, the opcode register will have some address, some operation like opcode to do. So for example, if we have 0 0 1, we might it might correspond to some instruction that we are the one who created, and I'm going to do that right now. I'm not going to do all of it, just a bit, just an example to keep the flow going. So the instruction of 0 0 0 0 nothing is do nothing or something like that, or do some like any specific instruction over there. And now we have the instruction number 1, which is 0 0 0 1. What we're going to do, let's call it load A. So if load A instruction is very common, is to take the value from the RAM and put into a register that we call it the register A, to do something with the ALU later, to do some like calculation. So we know that to retrieve from the RAM and put into all of those registers, it takes like multiple steps. It's not only one step. So that's why we have another clock. So first we have a big clock over here that run the entire computer, and then we have another component. It's not actually a clock, it just take the clock signal and work with it. So the second clock, I call it, should be like, basically it's not a clock, it could be a program counter instead of clock. So but the second program counter can be like from 0 to 7 or 10, which means that every address of program counter, the second program counter will run extra step in order to do all of this task, what we see over here. So one instruction, this might be only one, but we might need extra step to work. It's like for the instruction to work. So so many things talking about it right now. Why it doesn't go back? Now it go back. So basically with the, let's delete this 0 1. So the instruction of 0 0 1, the instruction of number 1, we might have the time step 1 in it. This is the bigger one, and we have the smaller one, which is the time step 1. What we're going to do, we have the second step, we have the third step, and we have the fourth, and we have the rest. But it's only in a fixed amount of step, so we can put it into 7 or 8, depend on the some instruction that has the most time step needed. So some instruction might need a lot more than load, because load we just read from RAM, put into register. But there is some instruction that require multiple time step more than that. So let's say that our our instruction that need the most time step is the time step itself is 7 step. Let's call it like that. So every time our second program counter run to the second step, 7 step, it will have to reset back to the first step. And any instruction that don't require like 7, if it run to the second step and it finish, we can just say the third one, the fourth to the 7, let's say do nothing and wait until it restart back in to continue the step, to continue the main program counter. But we can check if it do something or not, and that is what I'm going to do after we design all of this. So the step one of our, say, load A, because that is the only one I can think of. So load A, we have to, what are we going to do? We're going to, what is this? Oh, this is clock. So our load A has sub opcode, which is we assume that we retrieve it because I skip entirely from the sub opcode. So let's assume that the sub opcode for the load A instruction already load into the sub opcode register. So sub op register is already load in there, and then what are we going to do is to first of all output enable the sub opcode. Okay, so we output enable the sub opcode. This one is sub opcode. Oh, we don't have enough space, so let's call it sub output enable, and then we have to read enable from the RAM, and that RAM is the value 1, not the instruction. So we have to enable the VE, put it green, let's just call it VE, so the value RAM enable, and then we have to tell the RAM to read enable because we want to read some value from the RAM. So one time step we can do 3 instructions at the same time. We just need to enable those wire with physical, like actual electricity for it to work. So now the value, oh, we not actually read, we have to put it into our address first, address register. So it's going to be RAR, put it in gray, address enable, and yeah, so that already used the entire bus. So we have to wait for the next step for the bus to clean up before we actually read the value from the RAM. So the second step, we're going to read enable so where were we? Oh, yeah, the second step. So the second step is to read enable from our RAM. So it is RAM read enable. So the RAM read enable will take the value into the bus, and let's assume that we have the A register. For now we don't have yet, but let's say that we have the A register, so A rack, something like that, enable. It's not read, it should be input enable. I designed this very poorly. Like for the RAM we call it read, but actually we don't tell the RAM to read, we read from the RAM. But our opcode register is read too, so we call it read, but actually we take the value from the opcode, we read from the opcode. And now our RAM, oh god, oh here we call it read, but actually it's actually input to our opcode, and the actual output enable is over here, so we call it very bad. Rename it later, but for now let's say a register read enable. Yeah, so now it will put that thing into our register A1, the A. Yeah, that should be the step that required to do the load A operation. And we can see it's very simple. It's much simple, better than what I did over here. Control unit and blah blah blah. It's just some bad stuff. Decoder. It's just overcomplicated stuff. So yeah. So all of this thing will like represent in binary. So we can have, for example, our component is 4, we have another 4 which is 8, we have 2 more and 2 more which is 4, 3 times 12, so we need 12 bit to control all of this. So we can use multiple RAM to control all of it. So for now let's say I have it like this. I can represent it like this in a chunks of 4. So the first time step is sub opcode, what is it again? So actually, yeah, sub opcode output enable. So the sub opcode output enable should be one of these. I don't know which one, but let's say one of it. So we turn it from 0 to 1, and we have the value RAM enable. I don't know too which one of it, but let's say one of this. But it must be fixed. We cannot just put it this one, that one, but so one of this must correspond to that single wire for it to work next time. And then RAM address register input enable address, yeah. So it should be one of it too. Let's say one of this. I connect to one of this. Now we have 3. And then the second one should be the same thing but only 2, but it's different too because we have a different component controlling a different component, so it should be one of this and one of this. And now we come to the third one. The third one is nothing because our instruction already stopped at the second time step. We can keep our time to continue to the 7 and wait for it to reset it, but I don't want it to go to the 7 because if our biggest the instruction that need the biggest time should be like 15 or something, for example, it doesn't need that much, but for example it need up to 15. We don't want our computer to run the time step up to 15 if it already finished at the second time step. So what we can do is we use like NOT gate. We use a, I don't know what it's called, but basically it's just a bunch of NOT gate connect to all of this. So all of it has to be 0 for the output of all of the NOT gate to become 1, and then we can just use a bunch of AND gate for it to end all together. So if one of it is 0, which means one of it is 1, which means one of it has instruction like this, it's not going to skip. So if all of it 0, basically what I'm going to what I'm talking about is that if all of it 0, just skip the time step and then go to the next program counter. Yes, that is the meaning of life. Let's go. Shit. What I'm talking about. And actually we need the third time step. Actually I think the third time step is just to tell our program counter to increment by 1. Yeah. Yeah, so the third time step is or we can create, or we don't need to create a component to ask if it all 0, because it might use a lot of wiring and a lot of transistors, something like that. So what we can do is just create an instruction small code over here that whenever it go to the last one, it just tell the thing to reset, tell the time, the second program counter to reset itself. So it's actually very smart. So if it go to the 7 step, yeah, it doesn't matter. But if it stop right here, I can tell it like second program counter reset. So we should call it something like timer reset or something like that. So we reset the timer itself, but we need to increment it first. So program counter increment. So the reason that we increment it is because we want to get to the next thing. So after we increment it, we go back to this one, this thing over here. Basically a basic microcode to load instruction from RAM. Yeah, that's what it's for. So yeah, so it increment, it reset the time step to 0, and it also I want to reset the opcode register to make it all 0, so it doesn't interfere with some of this thing, because remember that all this is time step, and then in a single time step it keep asking what opcode is it to. So if our opcode is 0001 and then 1, it will do this. If it's 0001 again, but this time is 10 because it's the second one, it will do this. 0001 with the 11, number 3, it will do this. But this thing, it doesn't care what value in our opcode is. We can reprogram with every single possibility of our opcode could have the value, but our opcode going to have like 8 bits, so it 256 possibility, and we're not going to choose that thing to like that way of solving problem. We're going to reset it back to 0, so that now this one is 0000 call it 000 and time step 1 00000 time step 2. So we're going to have a opcode reset, yeah. I think everything seemed to be very good, so let's finish our drawing. How long have I been streaming? It's been an hour still. I talk a lot. Drink some water. So let's continue our stuff. This is the clock, where we don't really care for now. Basically the clock just connect to this one line. I think it just like a blink, blip blip blip, but it blink fast enough for the component to do their own thing. The computer we're having right, I'm streaming this computer. The clock speed should be around 2-3 gigahertz or something. Let's check it out, shall we? I don't think I can, because there's some confidential information in the computer itself. But let's say it's 3 gigahertz of clock speed. Basically gigahertz is G. I'm not sure how much is it. let's do a quick search. So giga 10 to the power of 9, so basically it does 3 with the 9 zero, so 6 9 3 million, isn't it? 3 giga. Oh, it's not a million, it's a billion. It's a billion, yeah. Call it a million. So it's a billion time per second. So every single time it runs 3 billion like clocks. So it could, like, for some calculation it need only 2 step or 3 step, but in a more advanced computer it might need more for some, like, it to control other component, but still it's need only like around 10 step, for example. So it's already done in sub millisecond, let's say. As I'm bad with number, but yeah, that is just to tell you how fast it is. And this is very weird thing. So let's continue with our stuff. I think we need to rename our input too. So input enable, and this is output enable. Oh, we forgot to talk about the sub opcode. But sub opcode doesn't matter. Oh, sheesh. Yeah, I'll talk about it later because I think I'll figure it out. So this is read enable. Basically, the read enable is the output enable, it's not read. The naming convention is horrible. Let's rename the entire thing, shall we? This thing is not VRAM value RAM enable, it is value RAM select. So it's just the way we select the VRAM or not. So if it not, it will automatically select the instruction drive. And the RAR, it is address input, so just call it input enable. Yeah, and this one is output enable and write enable. Write is update our RAM. Yeah, this is what we're going for. And this is, I just want to clean it up a bit. Look horrible. So it is output enable. We have the increment and we have the jump and we have to reset. Yeah, so that is what we need for the thing. And I also want to clean this because I just write it down and now I clean it up. Very bad thing. Input enable and output enable. So register just read in, put out. I don't think we need to output the opcode into our thing, into our bus. We don't even need to do that because our opcode is directly connected to the ROM chip. We don't need to output it here to read it from the ROM. That is require another step, but that step must be controlled by the ROM. So if the ROM doesn't control, it will not output, so the ROM cannot get a value, so our computer doesn't work, so we have to connect it directly. So we don't need the output. What we need is the reset. Reset, basically put it back to 0. And we will talk about the output later if we need, but for now we don't, so why bother? So this is another 8-bit connection. let's connect it to the ROM down here instead. So what color should be our ROM should look like? Should be. English is horrible. So this should be, let's call it different than the ROM because it is microcode. Let's call it micro ROM. Microcode ROM. It is the ROM that store information about microcode, about the instruction, and it has 8-bit input. It's not 8. I think there is more, because our time, like the time I'm talking about, the second program counter, we could use like 4-bit for the 16 step, but I don't think we need up to that 16 step. We can use like 3-bit for 8 step in maximum. So this should be only like 3 step of time, and then we have 8-bit of instruction. Wait, what is going on? What should we use? So what I have in mind right now is that our opcode is 8-bit, and we have additional time step, let's say 3-bit. So now we have 12 in total. Oh, not 12, it's 11-bit. Horrible at math. So 11-bit, that is, if our, wait, so what's going on over here? Let's mean that our ROM address will have to be bigger than 11 in case we use like 3 time step, not a 3-bit time step. So let's see, what ROM can we use? 16-bit one. Oh no, it's not 16-bit. The ROM should be like 4-bit or 8-bit, it doesn't matter. I prefer 4-bit because we can split our chunks into 4, but let's say it's 8-bit by 16-bit ROM. So 16-bit is 16-bit of address, I think. I always said I think, but 16-bit is, that is a lot. 8-bit ROM, let's just say search for 8-bit ROM. Can I use? It's not ROM, it's EEROM. EEPROM. Erasable electrically programmable read-only memory, which is a horrible, terrible name. We're having trouble again. Cannot find. Oh, what is this? A very slow one. So let's say there is a ROM that has 16-bit of address, because it's only like 4-bit, 8-bit, and then 16 is like double. They don't do like 12 or something like that. So let's say that our ROM is 16-bit. We can use 11 of it. That's great. Now problem solved by only imagine the solution. So now our opcode will input the like directly to our micro code ROM, and we have that 3 extra bit correspond to the time. Second program counter, that's what we need. So let's create the second program counter, the lighter one. I don't know what should we call it, but second program counter. What should we actually call it? No one in, oh, someone in the chat. Cannot see. Hello, hi. I don't know who's that, but yeah, hi. Probably he already got out from the stream because it's a very boring one, but so let's call it time stepper. Just what's going on with my brain? So let's call it time stepper. Stepper. That should be enough. STPER. That is the shortcut of stepper for now. So stepper is just another program counter, but a smaller one, a junior. It's like work only with 3 step, 4 step, or 7, 8 step max. And that time step will input into our microcode ROM as a additional bit of address. So basically every like instruction of our computer program is just an address in our microcode ROM. So if I give it the 0001, it's just the first instruction, for example. So that is the way how we store instruction in our in ROM, in our program. Just put it next to the thing so that it connects together. And our stepper need clock, and we don't care the clock. Every time the clock went in, we just increment the step. So every time the clock went in, it just increment the step. And we need input to reset the thing. To reset, what else do we need about this second program counter? We don't need jump. We don't need output enable because it directly connects to the microcode ROM. We have reset and increment. This is the increment, or the clock. And I just realized that our program counter, the main one, every time we enable the increment, we don't need the clock to increment it, I think. I think we can just put with the clock or not, I don't care, but this one is the increment and the clock is the same, so if the clock go in, it increment, doesn't matter. So that is the second program counter. The first one is 8-bit program counter, the second one should be only like 4-bit, 3-bit should be enough. I kind of want to make it 4-bit, but I don't think any instruction need that much of the step to work. Now the microcode ROM, read the opcode. Let rewrite our example again, I think. So for example, the load A, we already done our retrieve code. So the retrieve also store in our microcode ROM to retrieve data, the instruction. So after it retrieve, there's some set of instruction, like for example, let's say load A again. The load A is, let's put into address 1, and at the time step of 0, the first step of load A is to, we're not going to take the value from the RAM yet. Why? Because we don't have the sub opcode, the operand, which is very important. And now we have another component, another register. See, we use a lot of register in this design. So it will have the input enable, and it will have the output enable. It's not like the opcode register where it has only reset. This one will have to output it sometime when we want it to output it to the RAM to read something from the RAM or something like that. So, and we connect it to our bus. The bus is a bit longer and use a different color now. It's strange. Now it connects to the bus. So what we're going to do is to retrieve the sub opcode. We don't have it yet. So basically, to retrieve sub opcode is to increment our program counter by 1, because the way we store sub opcode or the operand is in the next line, not the, we don't split it into 2 different 4-bit like most of the tutorial on the internet talk about for about 8-bit. So we split it because I want the the operand to be 8-bit to work with multiple, like for bigger size of RAM. So what we're going to do is to increment our program counter, by the way. So it's a PC increment, and I kind of want to output it at the same time so we don't waste the time step. So I don't think we can. Let's say we can for now. So we change it, we increment it, we output it. The value might be go through a bit of a transition like what I said, so it might, but it doesn't matter because we're going to tell our RAR to input enable. That's what input enable to take the address in. And now we have to reset everything. Wait for the next step, 00001. This step we have to put this like this. So this step we already have the address, so we take the the operand from our RAM into our sub opcode. So basically it's going to do the RAM output enable, output enable, and then at the same time we do the sub opcode input enable to store it in. I think we're done retrieving the sub opcode, and there's a bunch of instruction that might need sub opcode, and they consist of the same like time step. Now we already waste like two steps to retrieve sub opcode, but I don't think that is a big problem. We still have 6 steps more to work with. So let's just pretend now we already have the sub opcode. Now we can do something with it. Basically we're going to get from the RAM and store it into our register A. So first we're going to take RAR input enable. I think we need to do the sub opcode output enable first, and then we put that value into our RAM address register by input enable it. Yeah, now we have the address. The step 3, we want to enable the VRAM. We select the VRAM. And then we output enable at the same time. Output enable, and then register A. Read enable. Input enable. We don't have the register A register yet, but I think that is enough. I think it's, yeah, everything is good. So let's clear it up. Now we have the sub op register. We need to register A, B, and other stuff. I'll make it black. So what do we need next? Of course, we need clock to connect with our sub opcode register. Or it's just messy, very messy. Let's say it connect like this. Doesn't look good, but yeah, it is the way it is. I don't think we should connect it, but already done. So now we have the input enable of the sub opcode. What am I doing again? What am I doing again? Yeah, sub opcode. Let's look around. I just forgot everything. Alright, now I remember. We have to design the register A simple stuff. So register A, just put it A, and this register we have to connect to the bus, and what I want to do is to connect it to the same bus, so it doesn't overcomplicate this thing, because it's going to connect to the same bus. So what is the point of connect the same different one? Like, we don't connect that, we put it like this. Yeah, so our register, as always, we have the input enable, and we have the output enable. And the same thing to the B one. But here's something I just realized. I might want to create more register C and D, in case we need to work with a lot of value at the same time. So if we do this, now we have 4, 4, 8, another 4, which is 12, and we have one more, 13, and we have another 4, which is 17 already. We cannot use we can do it this much, but I don't want to make it increasing so much the amount of wire we using. This thing is like, if I want to output from the register A, I will have to tell it output enable register A, and then output enable register B, input enable register B. But that's not what I want to deal with. So what we're going to do is, oh, it's too big. What we're going to do is we have the same input enable over here, and then we connect the output enable to the same wire. But then we have the selector, just like what we did with the RAM. So we select which chunks of RAM we're going to use. So we have B select this one, and this one is A select. And if we have more, we can just tell it D select, C select. But if we have more than 4 or even more than that, we can use a decoder. So I think if we have 4, we're going to have A, B, C, D. We don't need 4 wire to select 4 different register anymore. We can use only like two input, and we input it into our decoder. This is where the decoder could be used for. So it will output 4 different value, and only one of it is enabled. That is the reason. So if I want to select the register A, I can put a 0, 0. Let number it 1, 2, 0, 1, 2, 3. So if I want to select register A, I can just put 0, 0, which will output, when it decodes, it will output 1, then the rest is 0. So we only select one of this. And if I want to select the register B, I can put a 0, 1. Yeah, something like that. And it will output 0, 1, 0, 0, which means that we don't enable A, we don't enable C and D, we enable B. That is what I'm thinking about. I don't know why I have to explain all of this. So let's say we have only 2 for now, don't make it too complicated. And the clock. I start to become frustrated by connecting the clock, but it is the way it is. It is what it is. I should have done it from the start, like not connecting it at all. So the clock is everywhere now. What I can see is, the only thing I can see is red wire. So rat up. Now I think I want to finish this before we end the stream. I kind of want to finish. So our A and B register will have to connect to ALU, which is very important component. Most likely the symbol is like that. So let's do some research for some of you that don't know about ALU. So here is the symbol of ALU, and it's just made up a bunch of logic gate, and the purpose of ALU is to doing the calculation between binary and binary. It could be decimal if we could represent it in with some like electronic component, but our computer is 8-bit in binary, so we're going to use ALU, 8-bit ALU, and the only important part of ALU is something called adder. I think I talk about this many times. So adder is like, let's call it 8-bit adder. So basically it's just physical component, physical hardware. By hardware it's already physical, but it is a hardware that add two number together. So yeah, so we're going to find 8-bit adder. You can use like 4-bit adder because they don't have 8-bit, I think. Let's find 8-bit, maybe that's easier if we can find one. Chip. Well, it's just about the it's very horrible when you're trying to search for it. Okay, shopping. We have this subtractor, but I don't want the subtractor. I want to build a subtractor myself, because we're going to use the negative system called negative integer called 2 complement. And we'll explain it because I think I already explained it once. Let's look at this first. Yeah, basically just take some input and output, and we have carry in. Oh, somebody coming. Alright, let's continue our stuff. So we can use the 2 complement negative number system. So what is 2 complement? I don't know how many times I should explain this, talk about this. So the number 5 in binary should be 1 0 1 1 2 3 4 5. Yeah, I hope so. So it's 2 to the power 2 to the power of 0, which is 1 4, so it's 5. Yeah, so the number 5 in binary is 1 0 1. So if we want to represent a negative 5, which the reason why we want to represent negative 5 is just because we have only the adder. So we can take 5, like 5 add with 6 to get 7. But if I want to get 7, damn, to get 11. But if I want to take 5, subtract 6 from it. So if I want to do this, we still have to use the adder, but we convert 6 into a negative 6. So how do we represent a negative number in binary? So there's a lot of way, but the negative integer system that we're going to use is 2 complement. I think I spelled it right, complement or something. Yeah, let's delete it so no one see my mistake. So let's talk about 5 first. So when we turn it into negative 5, how are we going to turn it into negative 5? So this one way. So let's say our number is 4-bit. So here is 4-bit. So if I want to represent a negative number, I can inverse, like flip the flag side, this bit over here. I don't know what they call it, but I think it's inverse or something. So basically you can inverse the first bit and then the rest stay the same. The rest of our numbers stay the same. So now this one is negative, this one is positive. But when we try to add it, the reason we don't use this this solution is that when we add it, the result is wrong. So it's 1 1 0 1 0 1 0 1. So we have this is not it is not 0 because 5 negative 5 should be 0, but this is not 0, so we use 2 complement. I don't want to explain the 1 complement. Let's talk about the 2 complement. So I think to convert binary into negative number is to inverse every single one of this bit first. So it should be 1 0 1 0. So from 0 to 1, from 1 to 0, yeah. And then we add 1 to it in binary, so going to be 1 0 1 1, and this is negative 5. So if we try to subtract it from our, wait, how's it, oh yeah, if we try to do it again by using only adder, because we only have the adder, I don't want to use the subtractor, so we got 0 0 0 0 1, and this bit over here is just carry, so we don't care about it. The only thing we care is the rest is over here is 0, so 5 minus 5 0, so that is the right one. So let's find some examples. So 17 minus whatever 8. So let's convert into binary to make sure that our thing is working. So what is 17 in binary? I'm not sure what is 17 binary, so it should be 1 2 4 8 16. So it's 116. We have 1 left, so 1. So it is 1 0. Oh, now we have 5 bit. So let's not use 17 because let's talk about only about 4 bits. So it's 11 minus 8. We can use 1 of 8, 3 left, 1 of this, 1 of this. That should be right. I'm not sure. 2 to the power of 3 is 8. 8 plus 2 plus 1, yeah, 11. So it's 1 0 1 1. And I was in the number 8 in binary, so number 8 is 1 0 0 0, yeah. So now we have the number, and we have to convert this 8 into a negative number. So we invert everything, 0, and then we add 1 to it, so it's going to be 0 0 0 1. Is it? Let's do it again. 1 1. So that is what we got. So it is 1 0 0 0. It'll stay the same, isn't it? Why negative 8 is the same? That's very confusing. So let's see if it's working. So it's 1 1 0 0. And what is this? It should be 3. So yeah, it is 3. 1 1, so 2 plus 1 is 3. So 11 minus 8 is 3, is correct. Yeah. So some of you might ask, the way we convert a positive number into negative or negative number in positive, we have to invert every single thing, which is fine because we can use inverter. We can use one of this chip. Basically it's just a bunch of NOT gate inside. Let's call 8-bit. 4-bit, sorry, because it doesn't have that much of a thing inside. So the inside of this component is just a bunch of NOT gate, or some of it use XOR gate or other gate that could be working. I'm not sure they use XOR or NAND. They use NOT gate. So basically they just convert if it's 1 to 0, if it's 0 to 1. That's fine. We can convert this 8-bit or 4-bit, whatever. But then you might want you might ask, we have to add one more single digit into this inverted number, and then we have to use like, that means we have to use extra step inside of ALU, but we don't need to because our adder, so the way we add in binary, we have something called the full bit adder. It's like, I don't know, I don't want to explain it for now, but for example, this value add with this value, we have another input in called the carry in. Basically, the carry in is just like, we can put 1 if you want to subtract. So we can put 1 into the carry in, and that basically mean we adding 1 to all of this. That is not a problem. So every adder will have a carry in and also the carry out. The carry out is this one, extra bit over here. When we add it, we have extra bit. I think I already explained once about this thing in the last stream, but now I'm very exhausted, so I don't want to explain it again. So resistor A will have to connect to this. Resistor B. Oh god. I'll connect to this, and our ALU will have to connect to our 8-bit bus. So yeah, and there's some like a thing in here. So we have the clock. We need the clock. So our adder, their purpose is just add thing up. We don't care what input is going in. If the clock push, it just add some value and put it into our 8-bit bus. Or maybe we need another extra input to tell it if we want to add or not, because or output enable. Let's call it output enable. Yeah, let's call output enable to prevent in case like there is some value in there and we don't want it to output into our bus. Yeah, we can put output enable. So what else? So here is just the adder. And we can use the adder to build the entire ALU, and this is not ALU. I should not done this. This is ALU, but what we have right now is only adder. So we put another component between the register B in case we want to subtract. So that component is I think it's buffer. This buffer over here, control inverter. Yeah, they call it control inverter. Oh god, let's go back. We have a very good one. So I don't think we can put this on stream. So control inverter only invert the input only if we tell it to invert. So if we tell it to invert, it will invert, but if we don't, the input stay the same into our ALU. So if we wanted to subtract enable, like enable the subtraction, so if we enable this one, we can enable our inverter, control inverter, and then we put 1 into our carry, like carry in. That is what we're going to do, where we got the physical component to build it. But for now, let's just dream. Yeah, I think we done a lot of things. And yeah, we still need like some kind of flag register, basically store information about our calculation, because sometimes when we add some number in binary, it might overflow. For example, if we have the number in 4-bit like this, if I add only one more, like 1111, I add one more bit, it will overflow things. So 1 like this. So now it's not 4-bit anymore, it have extra bit, which is more than our computer can handle. Our computer can handle like 8-bit, but if we add it and it overflow more than 256, so 8-bit is for 256. For example, if I add 100 and 200 together, we get 300, which is not good because our computer can handle only 256 number. Now it is 300, so we have to we have like overflow digit of binary like this one. So that overflow digit will be like we can observe it by using the carry out from our adder. It's just a simple output from our adder. So if it overflow, we can tell our computer that it is overflow, and we can create an instruction to tell it like jump if it overflow. I'm not sure where when are we going to use the jump if overflow, jump if carry, that should be the right word. So jump if carry, I don't know when should we use it, but there's something called jump if 0. So the jump if 0 instruction is just if we have to store it into some register, so it will ask the value. If it's 0, it will jump into a specific instruction, the operand that we give them. If it not, it will not jump. So the jump if 0, we can use it to ask if the value in A equal to the value of B. So what does it mean? So we want to know if 5 is equal to 5 or not. Equal, we have to use 2. So if 5 is equal to 5, we can make our program jump back to some lines of instruction to make a loop or something. So if 5 equal to 5, how do we know if it equal? Because we don't have the component to ask if it equal or not. But we have the adder and subtractor, which is very useful. So what we can do is we take 5, which basically A, the value in register A, minus B, and the value should be equal to 0 if it equals. So 5 minus y is 0, but if it not equal, 5 minus 4 is 1, it is not 0. So we can take the result from our ALU, put into a specific register. Mostly they call it the flag register. So we can ask the flag register what the value of what is it. So is it 0 or not. So if it's 0, we can run our jump instruction. So that is what it is, and it is very useful. We can do the jump if negative, jump if positive. Jump if negative basically mean if one number is smaller than the other one. So if A is smaller than B, we subtract it, we gonna get a negative number because it's smaller. So we can ask it if it's negative, which means A is smaller than B, we can jump. If it's positive, not 0, we can jump. We can do a lot of instruction from this basic flag. Basically the state of the result from our ALU, from our calculation. Yeah, I don't think we need any other stuff right now. It's complete so fast, isn't it? We need clock, of course. So let's create clock real quick. I want the clock to be like controllable, like make the speed faster or slower whenever we want it, and stop it and push it. It's like what Ben either done with his like created. So he create a clock module basically with something called the 555 timer. It's a basic component. Here is it, I think. Here it is. I used the 555 timer before in my school. So the 555 timer using with the capacitor to like make a like a, they call it a stable multi-vibrator to make a clock signal, like make it blink, boop beep, something like that. And we can tell our clock to stop. So that stop also very useful if we like our program run to an end. The last instruction is stop. You can enable this one, boom, done, everything will stop. And what I'm thinking right now is that this computer is run internally, control its component, and we need some output, the way to receive like to perceive the information in our computer, what is going on. So we might need another register, and that register can use the value in it to control some other component like display or a monitor. In the future we might create our own like graphic card that could control a simple LED LCD monitor, LCD or something. So that is what we need. So let's create it real quick. Let's call it the output register. Basically it's just another rack. So if we input enable the thing, it will take the thing and can output it back if we want, but I don't think we need to for now. Let's not. And this thing will might need to connect to the display. To a display to output the value. So we can output our value like it is in binary, but we can output into like decimal by using some like a bunch of components to convert binary into a decimal to work with 7-segment display. That's what can be used, and it's also used by Ben Eater to output his information in the computer. So this is still the clock. I don't think there's oh, here is the output register. That's what I'm talking about. So he used a bunch of 7-segment display, and then there's some logic here to like control it. And I might want another kind of register that control other component. For example, we might want to connect our keyboard into our computer. If we get so advanced to the keyboard age, where we might have mouse control the mouse position in our display, our monitor. Not sure. We can use this computer to control another electronic device like a LED or a lot of stuff, like can put it into a IoT project, Internet of Things. But this alone is a masterpiece, we can call it. I want to build this on a breadboard like what he did. I also want to create it into like a circuit structure, a sculpture, I think. What is it? Electronic sculpture. I found it online. sculpture, how do I, yeah, they call it what is it? It just basically it is a functional circuit, and the body of that, like the thing, like a functional circuit, how do I say it, how do I call it, it's just an object, a working the object that the body, the skeleton, the structure itself is made of the circuit itself. You can see some of this is like, all of this structure is made of the copper, make it stand itself. So I might want to create a computer into this form, which is very cool, but I want it to be like modular, like replaceable, so that we don't have a lot of trouble like try to replace component if it broke or something. This is very cool if you can do this way. It's just ZAT computer, I don't know what is that, never heard of that, but it's kind of cool. But I don't want to make it into like this kind of PCB because I want to connect it with my hand. So the entire thing was inspired by Ben Eater, and I cannot go without mentioning the Crash Course Computer Design. So this series is very good at explaining how a computer works, so you should check it out. So I think it's the end of the stream. Tomorrow, or maybe not, or maybe next stream we're going to, like, I think we can redesign it in our schematic simulator, like this program that we can like create the entire computer inside that program and simulate it before we can actually build it. Yeah, that is what we're going to do. So let's close this, and the stream should be, oh, I don't want to go on because I don't think what we're going to do next. Yeah, so I don't know what to say, so let's just end the stream. Yep, bye.